To another video. So we just did a lot of work on sequences and series in class, and I'm going to run you through it. So we're going to look at a few theorems, and then I'll show you all the things we're doing today. We're looking at a few theorems, especially with like limits to infinity. And then we're doing the squeeze theorem. This is also to infinity. Then we're going to be looking at series, which is just like the sum of sequences. And then geometric series. So it shouldn't take too long. And I'm just going to be walking you through my notes because I don't have time today. But okay, so let's go. So the function theorem, basically, if you had a sequence like, let's say, like we have 1, 2, 4, 4, 8, 16, right? This is clearly like the nth term is equal to to the power of n minus 1. So the first one is 1 minus 1 is 0, so 2 to the 0 is 1. The second term, 2 minus 1 is 1, 2 to the 2 to the 1 is 2, that kind of stuff. And so what we can say is, in the function theorem, the nth term is just a function, right? Any term here, right, like 8 is the third nth term, right? Sorry, the fourth nth term, that's just a function. The fourth n, a to the 4, a4 is just equal to 2 to the 4 minus 1. And that's just a function. And so if any term inside a sequence is a function, we can apply any kind of limits or any kind of calculus to it that we're actually really good at. So for example, like if you try to find the limit to infinity of that sequence, and so you do n to the infinity, so it's the infinitive term of that sequence, and you do the limits and you get to 0 over 0, you get to infinity over infinity, you could still do L'Hopital's because each term is just a function. Okay, the next idea is the continuous function theorem. It's a little bit convoluted. I'm going to walk you through it, okay? But basically what it's saying is that f is a constant function, a continuous function at x equals L, and lim the infinite term of the sequence. This is what it means, lim n to infinity of a, n, basically a infinity, and a infinity is just the infinity term of the sequence. If the infinity term of the sequence is L, and we let that function of the thing is equal to f something, let's call it fx, and then at L, at x equals L, it's also continuous, then what we can do is we can do this limit trick, right? So we can have any kind of function of that term where lim n to infinity, you can put the limits inside the function like this. And let me see what I wrote here. You can take the limit outside. Yeah, you can take the limit inside the function, basically. So it's just a rule here. It's something to do with continuity, but basically, if you have this situation where you have lim n to infinity of the function of the term, you can put that limit inside as long as f is continuous out there, which it will be in most circumstances. So let's look at the first example we have. So does n, so this is the nth term, right? Does the term n to the power of 1 over n converge or diverge, right? So what we have to do in this case is we have this really tricky kind of like n to the 1 over n situation, right? If we were to take the lim from n to infinity of this, it would be infinity to the power of 1 over infinity, which is infinity over the power of 0, which is really tricky. It's not equal to 1, right? It's not equal to 1, but it's really tricky. And so what we do when we see a situation like this where we see that one of our variables, one of our parameters is the power, we want to kind of take the log of it. So we're going to use this theorem here, and we're going to do some funny limits trick to it. But let's just try to simplify this with some logs first. So we take the natural log, ln of a to the n, an is equal to ln n to the power of 1 over n, right? That's pretty simple. With the log rule, you could take out the power here. So you could take from 1 over n out to here to the front as a coefficient. So ln here, like this. And what you can say is the limit of n to the infinity of ln an is equal to the limit of the right side, right? Of this side. And so what you can do is that you see that this one, okay, so it's 1 over infinity is equal to 0. Ln of infinity is also equal to infinity. Let me give it a second. Well, technically, actually, sorry. You have ln of n here over n, and then you have ln of infinity is also equal to infinity over infinity. Here, infinity and infinity, you need to do L'Hopital's. So once you do that, it turns into this, right? So ln of n turns into 1 over n, and then that's over 1 over n. So you do L'Hopital's of the bottom one, n turns into 1. So what you end up with is 1 over n over 1, which is just 1 over n. And therefore, now when you do the limit to infinity, that's going to turn into 0. 1 over infinity is equal to 0. And now what we have is we have this, right? We have limit of n to infinity of ln of an is equal to 0. So what's the limit of an, right? An to infinity. Well, you can do this. You can take the limit inside, there, and then use e to the power of the whole equation to remove that ln from the left side. You get this. Lim n to infinity of an is equal to e to the whatever this is, 0, and that's going to be equal to 1. And so what we're doing here is we're kind of using the log to remove a really tricky part, and then taking the limit inside and then removing that log to be able to give us an answer. And this, again, this just means the infinitive term, the infinity term. Like this. So there we know the limit to infinity of the sequence is the final term at the end where it's equal to infinity is e to the 0, which is e to the 1. So yeah, basically this theorem allows us to solve these really tricky forms. That's the idea. Okay, now we're going to move to a different theorem called squeeze theorem. And in squeeze theorem, let's give us an idea. So A is a sequence, B is a sequence, and C is also a sequence. They're all sequences, right? But if we have A, n, which is a sequence, the first sequence is smaller than our target sequence. Let's call this the target sequence. So if A is smaller than Bn, and then Bn is also smaller than Cn, what we can do is that if we know that the limit of An is equal to L, and the limit of Cn is also equal to L, that means, you know, An and Cn both end up at the same point. Then if we are sure that Bn is smaller than Cn and then larger than An for all sufficiently large as n, then we know that the limit of Bn is also going to be the same as both of these two, right? And we can imagine it with this kind of graph. Obviously, it's not continuous. An's a bunch of different points. Same for Cn. But basically, because they're larger always, and Cn's always larger, and An's always smaller, and Bn is always in the middle, if Cn and An reach the same point over here, then Bn must also, okay? And so we can do this in some pretty fun ways. So, like for example, let's try to find the limit of n to infinity of this sequence, Bn, right? Which is equal to n factorial over n to the n. Basically, what that's going to look like is something like this. I'm going to rewrite it up here. So this is simply equal to n multiplied by n minus 1 multiplied by n minus 2, and that goes on until it's 3 to 1. This is all over n multiplied by 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 n. Okay, so that's what this means. So let's try to find a set of sequences that we can use to kind of squeeze this together. So we let an, the smallest one, be equal to 0, right? The limit of n to infinity of this one is, again, just 0 because it's a constant 0. And then we choose Cn is equal to 1 over n because 1 over n, right, lim of n to infinity of this is also going to be equal to 0 because 1 over infinity is 0, right? And so now we want to check, is this condition true? Is Bn larger than An and smaller than Cn at all n's? So what we're trying to do is we're going to do this, and I'm going to do it up here for you guys to see. So if we decompose Bn like this, we have n to the n, right, which is 1. Then we have n minus 1 over n, which is a number smaller than 1. And then we have n minus 2 over n, which is, again, a number smaller than 1, right? It's like 0.9, this one's 0.99. Whatever it is, it's smaller than 1, right? And we have that all the way until this one's also smaller than 1. This one's also smaller than 1, except this one here is equal to 1 over n. So we know for sure that this function is going to be bigger than 0. Oops. Sorry, guys. I don't know where I am. I don't know why it's like that. Okay. So we want to prove that it's larger than an. This function is obviously going to be larger than 0, but we also want to prove that it's smaller than Cn. What is Cn? 1 over n. Okay. So we have 1 over n right here, actually. But this 1 over n is multiplied by, like, let's say 0.8, and then multiplied by 0.9, and then multiplied by 0.95, multiplied by 0.99. So what we see here is that when it's n factorial over n to the n, what we get is actually it's going to be equal to 1 over n, right? This part here, the 1 over n, multiplied by a bunch of numbers. We multiply by 1 here as well, so it's going to be 1, and then multiply a bunch of numbers smaller than 1, right? And that's going to make it smaller than 1 over n, and therefore this condition where bn is smaller than cn is true. And so we know this is all true. And since, right, and since the limit of an and cn is equal to 0, and because they're all always larger than and smaller than, this condition is true for all n, then we know that the limit of bn is also equal to 0. So that's kind of like the use case of the squeeze theorem. So another example here is we want to evaluate the infinity term of sine n over n, right? So the way we do this is we want to use squeeze theorem, and we want to think sine n is always smaller than 1 and larger than minus 1, right? Because sine oscillates like this, and it goes on like that forever, right? And it never goes larger than 1, and it never goes below minus 1. And so what we can say is we can use those two things. So let's say let an equals to minus 1 over n, because remember sine n is always equal to or larger than minus 1. So we can think of the minuses here, minus 1, right? And so you have something like this, and then we let cn equals to something equals to 1 over n, because sine n is never larger than 1. And so you're here, 1 here. So sine n is always between these two. And remember, the theorem states that it's larger than, smaller than, or equal to. It doesn't have to be absolutely larger or smaller than. So this works. And again, when we do n to the infinity of this, it's 1 over infinity, that's equal to 0. So we know that the limit of sine n over n is also equal to 0. So that's the kind of beauty of this theorem, is that it allows you to kind of solve these really complex things. And you kind of just want to look at the form. You want to look at what kind of characteristics about it, like n to the n factorial over to n to the n. You know it's n, then n minus 1, then n minus 2. So you can see how slowly it's equal to 1, then it gets smaller than 1, and it gets even less than 1. So it keeps getting smaller like that. So you know what you can do. Okay, so that's the squeeze theorem done. Now we're looking at series. So series is just the sum of all the numbers in a sequence, right? So if you have a sequence a to the n of n equals 1, so it starts from term 1, term 2, term 3, and it goes until infinity. The series of this sequence is just the sum of all the numbers in. Okay, so the notation is like this. Basically the sum from 1 to the infinity. It's basically what I just said. Now, the questions that we often see with series is that what can we say about this infinity sum, like sum to infinity? What can we say about it? First of all, is it divergent? Or is it convergent? If it's convergent, what is the answer? Like, what does it converge to? So that's kind of what we often kind of have to find the answer to. So a way to solve series is that we want to create a sequence. We want to create, we want to create a sequence of sums, right? So imagine this. We have sk, right? So down here is the definition here. Let sk be equal to a1 plus a2 all the way until ak, right? And then we have a sequence of sk. So a sequence of sk would look, if we had the sum, if we had 1, 2, 3, 4, 5, and keeps going on like this, right? That's our a to the end, right? Now, sk is going to look like this. So when k equals 1, we're only summing the first one. So it's just 1, right? sk, right? It's going to be first is 1. And then when we have k equals 2, we're summing the first two ones. So what we do is 1 plus 2, that's 3. Okay, and then when k equals 3, we have 1 plus 2 plus 3, so that's 6. So we keep doing that until, so it stands to reason that if k is equal to infinity, that means that the value out here, let's just say, this is not convergent, but let's say it's like equal to 150, for example. If this is the sum to infinity, it means that the sum of all these to infinity is equal to 160. And s of infinity is also the infinitive term, the infinitive term of the sk sequence. And so we can do the same kind of things. We can still apply limits, right? We can apply limits. It's just that we're going to be doing the limits with a sequence of sums rather than a sequence of these. But it's still the same idea. And the reason why we do this is to be able to do math with it, is to be able to use those same limits in calculus, just like we were doing with the sequence stuff. So let's look at some examples. But yeah, basically it's technically called partial sums. So the sum until 1, the sum until 2, the sum until 3, the sum until infinity. They're all partial sums. And so, yeah, we're changing the problem to finding the limit of a sequence rather than finding a limit of a sum, right? Which we're really good at because we're really able to find the infinity of term of a sequence. It's really easy for us, right? Okay, so if there is, oh, and another part, if there is an answer, if sum of infinity is equal to 0, for example, then it's convergent, right? And if sum of infinity is equal to infinity, well, then that's divergent, okay? Okay, so let's try to find the infinity sum for this sequence, which is 1/2 plus 1/4 plus 1/8 plus 1/16. So the idea with doing this, I'm just going to walk you through it because in the end, you just need to know the equation. But what we're doing is we let sk, okay? So sk is going to be equal to 1 over 2 plus 1 over 4, right? Plus blah, 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 to 1 over 2 to the k. Does that make sense? Because this is just 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 1, 2 to the 2, 2 to the 3. It's just 1 over that. So it's 2 over k. And now let's do another one where it's a 1/2 sk, which is equal to 1/4, 1/8, and then 1 over 2k plus 1 over 2k plus 1, right? And what you can do is you see how the second term of s to the k, second term of the sk, and then the first term of the 1/2 sk cancels out with each other, right? 1/4 minus 1/4. The next one would be 1/8 minus 1/8, 1 over 2k minus 1 over 2k, except that this one has an extra 1 over 2k plus 1. So what you do is you let sk minus 1/2 sk, so you let those cancel out, and what you have is 1/2 and then 1/2 and then minus 1 over 2k plus 1, which is what you have here. And so if you factorize this out, you have sk equals 1/2 minus 1 over 2k plus 1, 1 minus 1/2, and the infinity sum, you just take, literally you just take the lim of k to the infinity, which is same here, lim of k to the infinity. And what you can do is 1/2 minus 1 over 2 to the infinity. Okay, that's 1/2 minus 0 over 1 minus 1/2, which is 1/2, which is what you have here. 1/2 minus 0 over 1/2, that's equal to 1, right? So this is kind of what we want to do is we want to be able to do limits on it, just like how we were doing with sequences, and this is why we do this conversion. Okay, and this is just a really cool idea of what we were doing. So if we had a square, right, of sides 1 and 1, okay, the total area is 1, right? Total area is equal to 1. Okay, and then we can subdivide the square, and what we were doing was basically we're saying 1/2, right? 1/2 the square plus 1/4 the square plus 1/8 the square plus 1/16 the square plus 1/32. So all of these little square subdivisions, right? All of them add up to 1, and it's 1/2 plus 1/4 plus 1/8 plus 1/16, exactly what we were doing. So it's just another kind of idea of what we're doing here. And this is actually something that leads into something called geometric series. Okay, so geometric series just means that it's in the form 1 plus r squared plus r cubed plus r4. And this thing right here is called the common ratio. Okay, the idea of the common ratio is that basically like you can see here. So the sum of all of this is equal to 1 over 1 minus r, and it's a little bit similar to what we're doing here. If you do, let me see if we have proofs for that. Yeah, here it is. So if we had an infinity sum of 1 plus r squared plus r cubed, you can do that same thing where you're multiplying r here. And again, like this, it cancels out. We have rk minus 1. Remember, this is technically r to the 0. So down here, if it's s to the k, sk, it'll be rk minus 1. And then here we have rk. So then all of these cancel out, these ones, and then it cancels out to this. You divide this to this side, and then what you get is sk equals 1 minus rk over 1 minus r. Right? And the idea is that if r, the magnitude of r is less than 1, then there is a limit. First of all, it's convergent. So if this is true, it's convergent. And I'm going to tell you exactly why it's convergent. So if you imagine we had 1 plus, and then let's say r is equal to 0.5, right? We have 0.5 squared plus 0.5 cubed plus 0.5 to the 4. What's going to happen here is 0.5 squared is like 0.25. And then this one's 0.25, and this one's a really small number, like 0.125 or whatever, right? It's probably like 0.0 or something like this. But it gets smaller and smaller until you're just adding zeros. And so it'll be like 1.8 or something, I don't know. But basically, when the r is less than 1, that's when it's convergent. there's another variant of this, which is when we have a r to the k, and this is a type of question where sometimes they'll say instead of starting at 1 plus r squared, instead of starting here, sometimes they'll tell you to start from r to the 4, like for example like that. So you have to calculate the sum to infinity of this chunk, but without this chunk. So basically the formula for that is where k is a starting number, you have k here. So basically ark is the first term, and what you're basically doing is you just take ark out, right? Let's say k here is 10. If you're starting from k equals 10, then here's ar10, you take that out, and then what you have here is I'm gonna keep it as k just because it's like to keep the algebra right. But basically you just take ark out, then that's 1 plus r squared plus r cubed. It's the same thing here, right? So you still have, as we proved, the sum of any k is going to be 1 minus rk over 1 minus r. And then you just times here. So it's basically ark multiplied by whatever it was. So 1 minus rk over 1 minus r, right? And then I think if we explain that, yes, so ark, so the idea is that if r is less than 1, right? If r is less than 1, so if r was 0.5, 0.5 to the infinity is going to be equal to like 0. And the reason why is because 0.5 is like 1/2, right? So 1/2 to the power of infinity, that would be 2 to the infinity, and 1 to infinity, which is just 1. And this is going to be 1 over infinity, which is equal to 0. So any number where r is less than 1, what you have is 1 over rk, but then this one goes to 0 if it's r less than 1. And so what you end up with 1 over 1 minus r. And so when we have this here, what we're multiplying by, if r is less than 1, is we're multiplying by 1 over 1 minus r. And so what you end up with is ark over 1 minus r. And this is also the first term. So you can also think of it as u1 or the u10, depending on whatever the question asks you to start from. But yeah, that's in this equation, you can use that to find the sum to infinity. So for example, like the sum to infinity of 2 over 3 to the n, right? So it's 2 over 3 plus 2 over 3 squared plus 2 over 3 to the cube. Notice how it starts from 2 to 3, 1, and not from 1, right? You're not starting from 1. So you have to use this form. You take 2 over 3 out, which leaves you with 1 plus 2 over 3 squared, would be 1 plus 2 over 3 plus 2 over 3 cubed plus that. So that it's this form here, ark, 1, and ark is just the first term. Remember, the idea is that we took ark out. So whatever we took, we multiply back in. So then this is just going to be 2 over 3 multiplied by that 1 over, and remember, because 2 over 3 is less than 1, therefore the minus rk, that's going to turn into 0. So then you have 2 multiplied by 1 minus r, and then the equation, and then what you're going to end up with is 2 over 3 over 1 minus 2 over 3, and then you can see how I did the math here, that leads out to 2. So it is convergent, and it converges to 2. Meanwhile, for this one, you can see here, the common ratio is 3 over 2. 3 over 2 is equal to 1.5, which is larger than 1. And what you're going to end up with is you're going to end like 1 plus 1.5 plus like 3 plus 5, and it just keeps going up and goes to infinity. So then it's divergent, it goes to infinity. So yeah, sorry if that was a really long video, guys. We covered a lot in class, but hopefully all that explanation was really helpful. And generally, you just need to know this equation here, but more so, I think more importantly, you want to be understanding what we're doing here, where we have, like, for example, we had 2 over 3, right? We had, we had 2 over 3, and we took 2 over 3 out. That's the idea. We took 2 over 3 out. This one is going to be equal to 1 over 1 minus r, and then you multiply 2 over 3 back in. That's the kind of idea I want you guys to take away from this. But yeah, okay. Thank you guys so much for watching. Have a good rest of your